Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In this video, we're finally going to connect all of the statistical properties that we have seen so far. Statistical property 1 about accuracy, statistical property 2 about precision, which finally gave us the expressions for the variances of the beta 1 hat and the beta null hat. Statistical property 3, which made sure that it gave us an unbiased estimator for the sigma square that we used to compute the variances of the beta 1 hat and the beta null hat. To finally concluding to the statistical property that is the one that you have probably heard the most during class, and that connects to the Gauss-Markov theorem. So as we've done with all of the other statistical properties, what are the assumptions that need to be fulfilled for the fourth statistical property? And the answer will still be the same as what we've said for statistical property 2 and 3. We need to make sure that assumptions 1 to 5 plus homoscedasticity are fulfilled. And there is a reason why I'm not writing assumption 1 to 6 and saying assumption 1 to 5 plus homoscedasticity. And it's because homoscedasticity is such an important and vital assumption for the Gauss-Markov theorem that it needs to be emphasized. Just like for instance, statistical property 1, we emphasize the zero conditional mean as the one being the key that drove statistical property 1. For statistical property 4, so the Gauss-Markov theorem, the one that drives everything is the homoscedasticity assumption. Because under homoscedasticity, we can say that among the linear unbiased estimators, OLS is the one with the lowest variance. Most of you might have heard your class teacher or lecturer say that OLS is the blue estimator with the lowest variance. Now, what the Gauss-Markov theorem gives us is a very important insight, and that is you cannot improve an OLS without giving up linearity or unbiasedness. And in here, you can make finally a little bit the connection with the previous video where I explained to you how and why do we need to change the formula for the variance of the beta 1 hat when we move from a single regression to a multiple regression. Because remember, when we did that, we explained that adding irrelevant regressors will increase your variance, but even in the cases where we would have added relevant regressors, because of that penalty item in there, 1 minus rj squared, you are still going to increase the variance of your beta. So what does that mean? You are trying to add an x variable to make your model better because you believe that adding this new variable is going to help you explain more the variation in your y variable, but at the same time, you are increasing the variance in your beta 1 hat, okay? So this is also the reason why you will see once you move on to more complicated ways of estimation compared to OLS, that there are actually other methods that can beat the OLS. For instance, the GLS method can beat the OLS, but is not unbiased in the same class. And keep in mind, in another video, I have shown you that OLS is actually not the only way that you can go about estimating a regression. And you've got the entire weighted least squares class, but in that weighted least square class, the OLS is going to be the most efficient one only under homoscedasticity. In the case where you have heteroscedasticity, you will prefer the GLS. So this brings us back to the fact where I kind of emphasized this homoscedasticity assumption in here and why it needed to be repeated all of the time in there. It's because if you have heteroscedasticity, so let's say that homoscedasticity is violated. What happens is that the OLS is still unbiased. Okay, so it seems one of the two characteristics for which we love the OLS, it's still holding. However, the second one, which should be precision, consistency, it's not been fulfilled. Okay, so it means, but it's not the best. And in this case, we're actually going to prefer the GLS to the OLS, because the GLS is the one that it's or a weighted OLS as well, because they would give us the lower variance betas. So Gauss Markov is about efficiency, but only under the homoscedasticity assumption. Before I conclude this video, I also want to show you a little bit a visual representation of what I mean with this high variance or small variance bias unbiased. So visually, how would you see whether an estimator is unbiased or it has high variance or low variance? Because sometimes you might be asked to pick between two different estimators, and very likely, if the question is a tricky one, you will be asked to actually choose between the two characteristics that we like about the OLS, which of the two you would be more likely to sacrifice. And keep in mind, I'm going to give you the answer beforehand, and the answer is that there is no best answer in here. It really depends on what you want to do with your study. But if you have to take a decision between sacrificing unbiasedness or sacrificing the precision, then you have to at least know what these estimators will look like. So let's say that a very good estimator would have, let's say, this kind of distribution. So remember the exercise that we used to do, taking random samples from the population, collecting the beta, and having that list of the betas. Well, now we're gonna put them into dots in here and find out what the distribution of that beta is. And let's say for an unbiased estimator, obviously the mean here has to correspond to the true beta of the population, okay? So what happens actually when you have an estimator that is actually unbiased? Well, if it is unbiased, it means that on average, it's not hitting the true beta. So you could have something that it's identical actually in terms of distribution. So the variance in there is not changing. However, you've got a beta that is unbiased because biased because the mean in here is actually going to fall under some beta, let's say, prime that does not coincide with the true population beta 1 that we have right here. So although in terms of like precision, this new estimator is as good as the previous one that we had, it's biased, and we obviously between the two are going to choose this one. Now, if we have another situation where actually, and I'm going to show this to you, where now we still have an unbiased estimator. So it's going to fall like the mean under the beta 1 that we had in there. However, let's say that this is what the distribution looks like. So it's got these thicker tails, this distribution, okay? And it's not as centered here around the beta 1 of the true value as we would want. So as you can see, because of the thicker tails, it seems like, well, this is where like most of the values fall. So clearly this new estimator that we have in here, this is unbiased because it's still the mean in beta 1, but not as precise. Okay, so between the black one and the orange one, obviously we are going to prefer the black one again. However, your exercise might not be as simple as choosing between the black distribution and the orange one, or the black and the purple one. It could be, well, which one is the best between the purple and the orange one? And your answer in there is going to be very detailed, and you will have to argue very well which of the two you'd rather sacrifice for whatever your result is needed to be achieved. Okay? Hopefully this gives you a little bit of a better idea of like, what do we mean with unbiased betas, beta hats, and precise or not precise beta hats. But keep in mind, the Gauss-Markov theorem was the one that told us that the OLS is blue. So if all of the assumptions are withheld, normally you would have with the good kind of estimation, beta 1 hat, that has a very nice distribution. However, if any of the assumptions obviously is not fulfilled, then you need to know which of them is not fulfilled for you to be able to pinpoint what is the problem that you're going to see in the end, and that's also going to help you to come up with a solution of how to fix that problem. Thank you for following this video, and I'll see you in the next videos.